Until now, we've been looking at what happens when we deposit a single value and let it grow. In reality, that initial principal is often supplemented. You might be investing regularly or repaying a debt. To treat the case of repeated payments, we're going to use the same concepts as compounding interest to build up our theory. So this financial object is called an annuity, and it occurs when we make repeated and regular payments. The type of annuity that we'll use most often is called an ordinary annuity. This is one in which payments are made at the end of each term. Now, dual to this is an annuity due, and this is an annuity wherein the payments are made at the beginning of each term. So an important point to immediately recognize is that there are now two meaningful periods. There's the payment period, which tells us how frequently we supplement our initial principal, and our usual compounding period, which tells us how frequently the principal compounds. There's no reason to suspect that these should be the same, so be sure to look for the periods in any problem statement that you get. So let's choose a concrete example though. Let's suppose that we're working with an ordinary annuity, and that there are regular payments of $R, and we're compounding at a rate of, say, little r. So I mentioned that the payments and compounding periods could be different, but for simplicity and this example, let's assume that they coincide. So we're going to draw our trusty timeline, and I'll fill in 4 compounding and payment periods. So the length of each of these things is a corresponding term, and I'll throw in big R and little r as a reminder to when they occur. And since this is an ordinary annuity, our first payment occurs at the end of the first term, and so doesn't pick up any interest. Now, as usual, as we move through to the next compounding period, we pick up a 1 plus R term, but now we invest another R dollars. The next term again sees everything multiplied by 1 plus R and another supplement of R dollars, and we continue until this fashion until arriving at the end of whatever period that we specified. So, I forgot to indicate what these values were, so I'll put that in now. All right, if we repeated this process n times, we would arrive at this big, long, ugly summation as a result of our future value. But what does the last term look like? So notice that in S3, the biggest exponent is 1 plus r squared, and in S4, it's 1 plus r cubed. So that suggests that the largest exponent is 1 less than the number of terms, which in this case is n minus 1. Now we can tidy this up a bit by using sigma notation, and if we really want, we can pull that big R term out of the sum. Now let's stop for a second and think about what we've found. We could definitely compute Sn from this formula, but it would be really tedious. Having to compute 1 plus r to the power of k for a bunch of different k's, then adding them all together, that's a lot of work. In fact, when less mathematically inclined people do this in real life, they'll often use a spreadsheet to compute these terms, then add them all together. But we can do better than that. So what remains here is a geometric series, and we know how to evaluate a geometric series using this formula. So if we take as our common ratio c is equal to 1 plus r, we'll plug this into our geometric series formula. Okay, so I'm going to start by rewriting down what we had before. And now everywhere that there is a c, I'm going to plug in a 1 plus r. The denominator, you can see, simplifies quite nicely, just leaving me with this r term. And so that was a lot of work, so you might have lost the forest for the trees. Let's summarize. If you have an ordinary annuity with payments of big R dollars compounding at a rate little r, and both the period types coincide with one another, then after n terms, the future value of the annuity is as follows. Again, it's worth pointing out how this is one calculation as compared to the n calculations we'd have to do if we had left this as a sum. All right, let's do an example. So let's suppose you're saving up for your retirement, and you figure your investments could see an APR of, let's say, 8% compounding weekly. If you invest $30 a week, how much will you have after 30 years? All right, let's do part B. How much must you invest each week in order to make $500,000 in 30 years? And finally, part C, if you make $50 a week, how long do you have to save in order to earn $500,000? Okay, So our first point is to compute the term rate. An APR of 8% weekly gives us this. Now for part A, we don't have to do much. We just throw everything into our formula. We're going to use a term rate of 0.08 divided by 52, and there are 1,560 compounding periods. We work out everything and it gives us 195,055.88. All right, this is a good return given that you only put in about 47,000, but you should ask yourself, without doing any mathematics, whether this amount is bigger or smaller than if you had invested the $47,000 on day one and just let it grow. Now for part B, we know what future value we'd like, namely $500,000. And this time we're looking for the weekly payments R. Throwing everything into our formula results in an expression which can be solved for R pretty quickly. Doing so gives us $76.90 per week. Now, part C involves the most algebra. This time we know every variable except for n. So for our purposes, let's let n be the number of years. And let's put everything into our formula. Now, since n is the number of years, we have 52 times n compounding periods. So to solve for n, we're going to isolate for the term in the brackets using some simple algebra. So here we have the 1 plus 0.8 divided by 52 to the 52n. And to bring that 52n out of the exponent, we're going to take a natural logarithm of both sides. Now we can use a logarithmic identity to pull that 52n out of the exponent. And now we can readily solve for n. And doing so is going to give us the following. We're going to have to use a calculator to work this out, but if you do that, you get 34.98 years, or effectively 35 years.